The final section of the book that has a new theorem in it is section 16.9, and it's on the divergence theorem. So it takes a while to state this and get this out, so let's go ahead and get started. We let E be a bounded simply connected region in R3, and let S be the boundary surface of E. Before we go any further, examples of this situation here are spheres, boxes, just any region in 3 dimensions where you have a solid region that has no holes in it and it's bounded, and what you're going to have in this situation is that the surface S will also be oriented. But you're going to get that from the assumptions here. So we'll see examples, and it's just sort of the simplest case with no holes, never an infinite region, but always bounded. Okay, so let F be a vector field whose component functions have continuous first partial derivatives on an open region that contains E. All right, now we're ready to state the theorem, or state the result. Then the surface integral f dot ds, which in this first equality is not part of the theorem, it's just part of what this means. The double integral over s of f dot n ds. And here's the theorem. This flux integral, the integral of the flow of f across the surface, is given by the triple integral over the region bounded by the surface of the divergence of f. So I'll make a few comments here. First, I'll just kind of reword the result. The outward flux of F across S is equal to the volume integral of the divergence of F over the region E bounded by S. I'm not going to prove this theorem. The proof is, a little involved and doesn't really, at the end of the day, give that much insight into using or understanding what the theorem says. So I'm going to confine my proof to the proof I gave earlier of the two-dimensional version of this theorem. So first, let's say it's also known as Gauss's theorem. And like I just mentioned, in 2 dimensions, the divergence theorem simplifies to this result that we've already seen. The line integral C of F dot N ds is the double integral over D of the divergence of F. Here, the assumptions in 2 dimensions are similar to the 3-dimensional assumptions. The region D that C is the boundary curve of cannot have any holes in it. So, and like I say, we've already talked about why this is true. I can find my discussion there intuitively. As you add up sources and sinks throughout the interior, how the vector field expands and contracts, if you will, down into a point, add up all of that business over the interior, and that gives you the same thing as confining your discussion to the boundary and just looking at how much is flowing across it outward. The final thing I'll say is, if you are a reader of the textbook, which I hope that you will over time, at least, struggle with, your math textbooks. It's difficult to read math. It's difficult for me to read math. Everyone, kind of struggles with the same challenges here. But I hope you will look at Stewart's discussion. Stewart states, and proves the divergence theorem for a more restricted class of regions. He calls these simple solid regions. And it's not overly important that you know the definition of these, but but it's a more restricted class than what I've stated here. Quickly, there are regions which are simultaneously type 1, 2, and 3, as he defined earlier in chapter 15. Like I say, but the theorem holds more generally. As I stated. Okay, so there are some best case scenario problems where using the divergence theorem is really quick. Along the lines of Stokes, it's often the case that the triple integral, the chapter 15 integral, is the easier one to evaluate. So oftentimes the problem will say, evaluate the flux using the divergence theorem. And what that means is go over here and compute the divergence and do the triple integral of the divergence. So that is what we will start with. We'll actually look at problem number 8 in the exercises, where we are given F vector field is x cubed y minus x squared y squared minus x squared yz. And S is the surface of the solid bounded by the hyperboloid. And the planes z equal to -2 and z equal to 2. So this is the given information, and the instructions are to use the divergence theorem to compute the flux. To compute the outward flux of F across S. Well, let's get our bearings on what this region looks like here. It's section 12.6 in the book where we get all of these different types of equations that, types of hyperboloids. Let's see, I like to rewrite some of these so that they make more intuitive sense to me. I believe this one, if I rewrite it, x squared plus y squared equals z squared plus 1, that helps me think about it. It tells me, here's the radius of a circle in the xy plane. And in order for there to be an actual circle, I need a number over here that's positive. I will always have a positive number regardless of z. When z is 0, we have a unit circle. And then for all other values of z, the circle just gets larger. So we're confined to the region from -2 to 2 for the values of z. So let's see. So parallel to the xy plane, it's always a circle. So we're going to have this sort of thing here. I guess I could get my, should I try to do something like this? Yeah. So this is the sort of hyperboloid of one sheet that would correspond to the given information. The surface includes 3 sides. The surface is the top, the bottom, and then the lateral surface here. Okay, so this is not going to be a straightforward triple integral. Let's see what the divergence is. I keep capitalizing when I should, not when I shouldn't. The divergence of f is partial with respect to x, so that's 3x squared y, plus partial with respect to y, that's minus 2x squared y, plus partial with respect to z, minus x squared y. Well, okay, I take back what I said. It's not going to be an involved integral because the divergence is 0, and that's what we need to integrate over E. So E is the region, solid region bounded there. So the integral, which is the flux, the integral across S of f dot n ds, is the triple integral over E of 0 dv, which of course is 0. All right, so it didn't actually turn out to be really any work at all. I mean, I guess you have to correctly get the divergence, but once you do, it's easy to see that the triple integral of 0 is 0. Okay, so we got more problems, examples to look at. We'll come back in at least a couple more lectures and do that.